So I'll start with a clinical background. Atherosclerosis is a chronic inflammation of the arterial wall that causes the narrowing of the lumen due to the formation of a lipid-rich plaque and an increased cellular activity. In this work, we focused on the superficial femoral artery, so in the context of the lower limb peripheral artery disease, which is the third cause of vascular morbidity and affects 200 million people in the Western countries. Among the various risk factors, hemodynamics plays a role, especially in the localization of the lesion. In fact, atherosclerotic plaques preferentially develop at sites of disturbed hemodynamics, like curved tortuous vessels and bifurcation. At these regions, as we can see from the pictures, a low or oscillatory Washer stress is usually observed. The role of Washer stress in the pathogenesis of atherosclerosis is mainly related to the modulation of endothelial gene expression. An high unidirectional Washer stress, which is considered physiologic in the range between 1.5 and 7 Pascal, promotes a quiescent and atheroprotective phenotype, while in presence of a low or oscillatory Washer stress, an atherogenic endothelium is usually activated. In this context, the aim of the present work was to develop a multiscale model of atherosclerotic plaque initiation and progression by coupling computational fluid dynamics simulation and agent-based modeling. The framework is shown. Starting from a three-dimensional model of healthy artery, the hemodynamics is computed and Washer stress are extracted at selected cross-sectional planes. For each of these planes, agent-based model simulations are run, and receiving the Washer stress in input, they compute arterial wall remodeling. After a certain period of time, the agent-based model simulations need to be stopped in order to update the hemodynamics following the geometrical changes. So a new three-dimensional geometry is built from the agent-based model outputs and the loop restarts. Starting from the computational fluid dynamics model, first a three-dimensional geometry is built with femoral-like features, and 10 planes are selected for the subsequent agent-based model analysis. The geometry is then meshed with tetrahedral elements and 5 layers of prism elements. And finally, a computational fluid dynamics simulation is run in a steady-state mode. At the inlet cross-section, a parabolic velocity profile is imposed with a physiologic mean velocity derived from patient's ultrasound images, while at the outlet cross-section, a reference zero pressure is set. Walls were considered as rigid structures, and no slip conditions were applied. So after the computation of the hemodynamics, Washer stress profiles were extracted at the selected cross-section and used to initialize the respective agent-based model. For each of these planes, agent-based model simulations were run, and they compute a physiologic or pathologic wall remodeling by simulating cell and lipid dynamics. I will now explain the working mechanism of the agent-based model. So first of all, the agents were cells, extracellular matrix, and lipid elements, and in order to replicate their behavior, probabilistic rules were applied. By implementing these rules, the model replicates cell mitosis and apoptosis, extracellular matrix production and degradation, and lipid infiltration in the intima, which are the main events involved during the atherosclerotic process. These events are also modulated by the interaction with the external environment, which is hemodynamics in this case. Finally, the present model is stochastic, and the Monte Carlo simulation is used to introduce a certain degree of randomness that characterizes biological system. Here we say the main assumption of the model. So first of all, we assume that the risk factors promoting the disease were already present. So the process of atherosclerotic plaque formation was purely driven by hemodynamics and Washer stress in this case. Then we consider a threshold for the Washer stress, so that a Washer stress profile is defined physiologic at a given cross-section if all the sides of the luminal wall are exposed to a Washer stress larger than 1 Pascal. While if there is at least one side that is exposed to a Washer stress lower than 1 Pascal, then the profile is considered atherogenic. In this slide, the agent-based model flowchart is shown. Following the initialization, the model implements at each iteration the cell dynamic, lipid dynamic, and geometrical regularization until the end of the simulated period. So starting from the initialization, a bidimensional hexagonal grid is adopted in order to implement the model consisting of a circular cross-section with 3 concentric layers, representing the intima, the media, and the adventitia. Then, to each site of the lumen wall, wall shear stress value is assigned, and in correspondence of sites exposed to a wall shear stress lower than 1 Pascal, an inflammation state develops, which diffuses through the intima as shown in the picture. This condition promotes the process of atherosclerotic plaque formation by perturbing agent dynamics. So then the model implements cellular dynamics, so cell mitosis and apoptosis, and extracellular matrix production and degradation. Under physiologic condition, a balanced mitosis and apoptosis, as well as extracellular matrix production and degradation, was set in order to replicate the homeostatic state of a healthy artery. On the contrary, when an heterogenic wall shear stress profile is applied, cell mitosis and extracellular matrix production in the intima are perturbed, as we can see from the red box, in order to replicate the increased cellular activity observed during atherogenesis in the intima layer. On the contrary, in media and adventitia layer, the dynamics are set at the basal end values. Then, Monte Carlo simulation is adopted in order to determine if an event occurs or not. So the CPU generates a random number between 0 and 1, and the event occurs in case this number is lower than its probability. If the event is inside the intima, the tissue rearrangement is inward-oriented, while in case the event involves media or adventitia, the tissue rearrangement is outward-oriented. Moreover, the tissue reorganizes following a minimum energy principle, meaning that cells move along the shortest path towards an empty space. The figure shows an example of possible reorganization of the tissue in case of production or removal of an element in the intima layer. If K produces an element, the intima grows towards the lumen, while if K is removed, its site is occupied by an inverse movement of the surrounding agents. Then, only in case of an heterogenic wall shear stress profile, the model implements lipid dynamics, which is computed as the probability of a site of the luminal wall to let the lipid enter. This probability increases with the level of inflammation and the number and distance from surrounding lipids. At each time step, only one lipid can enter, and also this event is regulated by Monte Carlo simulation. In this this figure shows a possible reorganization of the tissue in case the site K is the site of access for the lipid. Finally, the model implements the geometrical regularization at each iteration in order to retrieve smooth profiles. Before building the fully coupled framework, we verified the agent-based model behavior by running 10 simulations for 2 months. We need to underline that since the model is stochastic, a single simulation is not a representative solution, and so we need to run 10 simulations at least and evaluate the average behavior. So under atherogenic condition, the model was verified in terms of features of the generated plaque, plaque progression in time, and reproducibility of the output. On the contrary, when the model was initialized in physiological condition, it was able to replicate the homeostatic state of a healthy artery. From this figure shows how, starting from an initial configuration representative of a healthy artery, when the model is initialized with an heterogenic wall shear stress profile, all the simulations replicate a pathological wall remodeling with generation of a plaque that is shown in yellow. Moreover, although the intrinsic variability among the outputs, that is due to the stochasticity of the model, we can notice the reproducibility of the model. In fact, there is a good agreement among all the 10 outputs in terms of plaque location, plaque size, and plaque morphology, as well as the degree of stenosis and maintenance of media and adventitial layer at their baseline condition. This figure shows plaque progression in time, starting from an adaptive intimal thickening at day 15 until the generation of a lipid-rich plaque after 2 months of simulation. This final configuration is representative of a pathological solution and presents features resembling histological evidences, as for example the asymmetric geometry and a lipid-rich core. Coming back to the couple framework, we said that after a certain period of time, the agent-based model simulations are stopped and a new three-dimensional geometry is built. For this purpose, a method was developed in order to select for each plane the most representative solution among the 10 possible outputs. So for each of these outputs, the deviation from the average configuration is computed regarding the lumen radius, the external radius, and the plaque thickness, and the configuration which minimizes this quantity is selected. So for each of the selected configuration, the luminal coordinates are collected, and the new three-dimensional geometry is built by lofting the luminal curves. Finally, as regards the couple framework, we need to determine how often performing the coupling between the computational fluid dynamics and the agent-based modeling. For this purpose, we carried out a sensitivity analysis on the coupling time by studying 3 cases for a total follow-up time of 14 days. In the first 2 cases, the coupling was performed every 7 days and every 3.5 days, while in the third case, the first coupling was after 7 days and then every 3.5 days. The results were analyzed by comparing these 3 cases in terms of lumen area over time and agent-based model simulation mode at each coupling interval, which can be physiologic or pathologic depending on the computed Walsha stress. From the analysis, 2 scenarios arise. The first one involves those planes in which the Walsha stress values are far from the threshold, like plane 1 with very large Walsha stress and plane 9 with very low Walsha stress. In these conditions, the coupling period doesn't affect the results. In fact, we can notice a good agreement among the 3 cases in terms of lumen area over time, but also, as we can notice from the tables, also in terms of agent-based model simulations mode. In fact, the plane 1 always remain in physiologic mode, and the plane 9 always in pathologic mode, independently on the coupling period adopted. On the contrary, for those planes in which the Walsha stress is close to the threshold, the coupling period affects the results, not actually in terms of lumen area over time, as we can see from the graphs, but in terms of agent-based model simulation mode. In fact, the case B allows to catch switching behaviors that is ignored by the other 2 cases. This means that the case B, by updating the hemodynamics more frequently, is more accurate. Coming to the conclusion, in this work we developed first an agent-based model able to replicate the homostatic condition of a healthy artery, but also the morphological and compositional changes associated with a pathological condition. Then we built a fully coupled framework coupling agent-based model and computational fluid dynamics, able to replicate the mutual interaction between wall remodeling and hemodynamics during atherosclerosis. From one side, the process of plaque formation at regions affected by disturbed hemodynamics, and from the other side, the hemodynamics change following plaque growth. I would like to thank all the people involved in this project, from Politecnico di Milano, Politecnico di Torino, and Houston Methodist Hospital, and thank you all for your attention.